Okay guys, today's lecture is about the effective net area. So for the tension members, we talked about the limit states. The limit states, the first one is the yielding of the gross cross sections, which is straightforward. 0.9, that's the phi factor, times A gross, the cross sectional area, times Fy, the yield strength of the material you are using. The second one is rupture or fracture limit state. It involves more calculations. It is 0.75, that's the phi factor, times A effective, times F ultimate. F ultimate is the ultimate tensile strength. Now A effective is U, a shear lag factor, times AN. AN is the net area. AN equal A gross minus area of holes. So if we know how many holes we have and what's the diameter of the hole that we are intended to use, we subtract A gross minus the area of the holes. That will give me AN, and we explained this in the previous lecture. And we also covered the effect of staggering. When you have the holes staggered, not on the same line, we have potential path for failure, and we know how to calculate the staggered area. So AN, we covered it in details in the previous lecture. The only thing that's left for us today is the U, which is the shear lag factor. U, the physical meaning of U, if you are not connecting all the components of the cross section, all the components, like if you have an angle, it has two legs. If you connect the angle on one leg, we believe, or the results show that the section will not be effective all the section will not be effective in transferring the load. It means some areas will be has higher stress concentration than others. For that, the code applied a factor called U, the shear lag factor. The first thing you need to know about U is if all the components are connected, it means U equal 1. If not all the components of the member are connected, it means U is less than 1. How we calculate U is today's lecture. So if you look here at the screen, this is what I said. Now for calculating the fracture tensile strength, we need AE, and A equal UAN, where A is reduction coefficient for it's also called shear lag factor. The formula for U is 1 minus x bar over L. This will equal 0.9, but usually sometimes if you can calculate from the equation and you get 0.9, more than 0.9, you can use 0.9. And this is where the manual or the code specify the values for U for all kinds of sections. This is specification D. As I told you about the manual, guys, the manual, it is a manual and a specification. It's a manual and a code. The first few things here are about manual. It means they are giving you information about the sections, calculated strength for the sections, all kinds of charts and that. So when I say specification D, it means there's here, the last part is called spec here, which means specification. So if you open here, from now on, from here, it's a code. It's the specification. The specification number or chapter that covers the design of tension members is specification D. So if I go to D, so I start with A, B, C, so that's D. That's specification D. This chapter D, design of members for tension. So there is a lot of information here, and this is the code, the books. When you read in a steel design book, they refer you to these specifications. Then this is the table for calculating the shear lag factors of connections to tension members. So U equal 1 if all members are connected. Or you can use the formula I just showed you on the screen, 1 minus x bar over L. 1 minus x bar over L. Where L is the length, is the distance, is the length of the connection, which is the distance between the last bolt, to the first bolt in the connection, center to center. That's L. And x bar is the distance from the plane of shear transfer to the centroid of the member. I will explain this in more details. So they are saying this is for all kinds of W, M, S, and HB shapes. This can be used for almost everything, but alternatively you can use 7, 8, whatever you get from 7 and 8. For these cases you can use either the formula or the value, the allowed value or the permissible value in these sections. So we'll go, this is summarized for us in details in the following handouts I will show you. It's summarized and clarified for us, but this is your reference. This includes all the cases, and it includes cases for the welding, for the welded connections. This is for the welded connections. And this is for the HSS cases. Hollow steel section. It could be a rectangle, it could be a triangle, it could be circular, which is called pipe, because the connection to these members usually is unique. Okay, and this is for the angles here. And these are permissible values for the W, M, and S shapes. Okay, but the general formula is 1 minus x bar over L. Okay, let's go through these. So this is the formula again, 1 minus x bar over L. So if you look at the angle here, this angle, this is the plane of shear transfer. It means this plane is between the connecting plate and the member here. So your x bar in that formula is for the distance from here to the centroid of the angle. To the centroid of the angle. And you have to be careful. If the angle is aligned that the bigger leg is up or the bigger leg is down, you should know where to go in the manual and what you got. Sometimes, it depends on the layout, what you want is x bar listed in the dimensions. Sometimes you have it listed as y bar depending on the layout of the angle in the connection. This is what I'm trying to tell you here. And I also clarified this in the coming lecture. This is the T. If you are connecting a T like that, see, we are not connecting all the components. The components of the T is the flange and the web, this part of the web. So there is no connection in this web. So this is your X bar. Or if you are connecting a W shape, see, if you are connecting through the flange only. If we're connecting through the web also, U equal 1. But if we are connecting through the flange, this is X bar of the W. See, we deal with the W shape like two T's. So X bar for the W shape will be, look at its half. So it's the distance from the plane of transfer of load, of tensile load, to the centroid of the T or half of the W shape. So you are looking for this distance, X bar. And if you go to the manual, this distance you obtain it from the T made from the W shape. See? Then the value of X bar used will be the distance from the outside here. X bar equal Y bar in the structural T. So this value you are looking for, which is X bar in this formula, it's listed in the manual in a standard shape to be Y bar for the T made from this W shape. So these are also permissible values. This is a summary to this. See 7 here? 7 in this table. It's summarized for you here. They say, for W, M, or S shape with flange width not less than 2/3 the depth. It means here, B flange, the width of the flange, if it's greater or equal 2/3 of the depth of the W shape, U equal 0.9. Given that with flange connected with 3 or more fasteners per line in the direction of loading. So it must be 3 bolts per line, at least 3 bolts. If the flange width is less than 2/3 of D, U equal 0.85. Again, both conditions here, at least 3 bolts per line of connection. With web connected, if you connect to the web only, with 4 or more fasteners per line in the direction of loading, U equal 0.7. Now, if someone said, what if there is neither this or that? You go back to the formula. So the formula tells you either this or anything you get from this or that, depending on the connection. So this is if you connect to the flange, and here if you connect to the web. As you see, if you connect to the web, the section is not that effective. So U is very small, equal 0.7. So this is what you have in here, in this table. So this is the 0.9 and this is the 0.85. They are all saying all members having only 2 fasteners per line in the direction of loading equal 0.75. So those members, if you have only 2 bolts per line, use U equal 0.75. However, you can still calculate that from the formula. This is also a clarification. If you have an angle Okay, then if you have, this is the application of B flange over D if it's greater or equal to 2/3 of D, which is 2/3 is 0.66, and if it's less 2/3, this is 0.9 AN, and this is 0.85 AN, and this is for the angle. If you have 3 bolts, they are saying it's permissible to use 0.85, but if you have it 2 bolts per line, then it's allowed to be 0.75. Actually, these are modified, I think, in the 14th edition of the manual. So for the angle, there is single and double angles with 4 or more fasteners per line in the direction of loading, U equal 0.8. With 3 fasteners per line in the direction of loading, with fewer than 3 fasteners per line in the direction of loading, use case 2, but with 3, use 0.6. See, in this case used to be 0.85. I think this is no longer valid. So this table gives you the most up-to-date values based on the calibrated code. This is up-to-date code or specifications. You should always refer to this thing here. If you have a case that matches this code, that's good. If not, then this is your reference. This is the most up-to-date. That's why always you should be current. You should be always using the most updated version of the code. Then if you have welded connection, as I said, this is clarification of this part here. When you have welds, plates where the tension load is transmitted by longitudinal welds, only these are the cases. If length, this is L clarified for you, the length of the weld, greater than 2W, which is the distance between the transverse distance between the 2 welds, it's U equal 1. If it's L in between 2 and 1.5, it's 0.85, U equal 0.87. If L is greater than W, less than 1.5, U equal 0.75. You cannot use L apparently less than W. And they are clarified also, you can see them here. So these slides are clarification of the table D 3.1. So this is example analysis of tension. Remember, when you have analysis problem, it means things are given to you. You are just either calculating the design strength, or you are asked to check if this member will be okay under given loads. So usually sometimes the loads are given to you, the dead load, live load, wind load. So you apply the load cases and you calculate the maximum tensile force. Then you see if the section is good or not. This is typical analysis problem. So in this case we have W10 by 45 with 2 lines of 3/4 of an inch diameter bolts in each flange. So each flange has 2 lines of 3/4 diameter. They are using A572 material, which is not a standard material for the W shape. This is just an example. For W shape, we said we use A992, and he's giving us it's a grade 50. It means Fy equal 50 and F ultimate equals 65. These values are the same for the W shape, the A992 material. So use LRFD. This is not LEFD. This is LRFD. Correction specification. There are assumed to be at least 3 bolts in each line on center, and the bolts are not staggered with respect to each other. This case, there is a permissible value I showed you. This case, if B flange is greater or equal to 2/3 of D, for this section, we can use U equal 0.9, or we calculate 1 minus X bar over L. In this case, they are saying at least 3 bolts. When you have at least 3 bolts, it means the distance between the bolts is 4 inch. I will bring it to you. So they are saying at least 3 bolts, and the distance between each 2 bolts is 4 inch. So the length of the connection is 8 inch. So we have U equal 1 minus X bar over L. In this case, L equal 8 inch. So L equal 8 inch. So the only thing we need to find in order to calculate U for this section is X bar. And X bar for the W shape, we obtain it from the T sliced from this W shape. Look at the W 10 by 45. You see we have W 10 by 45. if I divide, or if I make two sections equal section from this W, so when we say W10, the number 10 means the depth in inch, so that's 10 inch deep, and the 45 is the weight in pound per foot. So when I make it or slice it into half, it will be 5 WT, it will be a T, 5 times half the weight, so it will be a WT 5 times 22.5. This is what I need to look in order to find X bar, and I will show you how we get X bar from this WT. So the following, if you go back to the example, you go to the dimension table, dimension section in the code, dimension, which is the first thing. The first thing is the dimensions. This will give you, see, here, DIM for dimensions, give you all the information about the geometric information and the areas, moment of inertia, centroid for all these sections, all the sections. So you will obtain. So if you go, let's just go there. W10 by 45. W10 by 45. So this is the W. So we have 10 by 45. A gross is 13.3. As you can see, it's 13.3 in here. D equal 10.5, which you can assume it 10, but the actual D is 10.1, as you can see it here. Okay, the code will not say it's like W10.1 by 45. They give you they round it to the best number so that you can use it. And B flange, this is the flange. The width of the flange is 8.02. Here you have it. And the thickness of the flange is 0.62. And these are the information given to us from the table. Easy to find them here. Usually these are not given to you. You have to go to the dimension section in order to obtain them. So it said calculate the tensile strength or the design strength. So phi t pn equal phi fy. This is the yielding. Straightforward. 0.9 fy 13.3. We get 598.5 kip. Now the fracture case require U and the area net. So A net equal. So we have 4. We have to subtract the area of 4 bars because in each flange we have 2. So this is the flange, the top flange. You have 1 bolt here and 1 bolt here. So 2 lines. So we have 1, 2, 3 in the top line, in this line, then 1, 2, 3 in this line. Then at the bottom flange we have the same. So if the failure occur like that in your cut, you will see 4 bolts. So we have to subtract 4 bolts. So the area is 13.3 minus 4. The diameter plus 1/8 of an inch, and we explained why we add 1/8 of an inch. Times those bolts are in the flange, so you multiply by the thickness of the flange, you get AN equal 11.13 inches square. What you need now is to calculate A gross. You need to calculate U. So you need to find X bar and then calculate A effective. So the X bar, we need to find it from the T. So we go to the T's. I guess it's it's after the angles. So we need WT, we said 5 by 22.5. So that's a T 5 by 22.5. 5 by 22.5. Okay, now look at this information given here on for any section. This is your key. This is your reference. So the A, D, TW, TW, the X bar, the R, Y, Z, all of these are based on this one. So in our case, we want X bar to be from the top flange to the centroid. Look at this. He listed to you as Y bar. You see Y bar from here to here. That's Y bar for the T. And that's what is the X bar that I want for the section. See? Y bar here listed. It's from here to here. All of this. And this is the X bar that I want for the W shape in order to calculate the U. In order to calculate the U. So I need Y bar. And this is my Y bar here. Okay. So I go to the W 5 by 22. So that's my section, 5 by 22. 22 and a half, sorry. So we go to Y bar is 0.907. Okay, be careful, don't get X bar. Be careful. Okay, so 0.907, as you can see, it's 0.907 divided by 8. I told you that's L. You get 0.89. Now, if you check the permissible value, we said this case is a W case with at least 3 lines per three fasteners, 3 bolts per line. If B flange is greater or equal to 2/3 of D, which is 0.66 times D, which is 10, then you can use 0.9. As you can see, B flange is 8. 2/3 times 10, that's about 6.66. So B flange is greater than or equal 2/3 D. So we can use 0.9. So either of them. So he will use 0.9, then and we have AN, then A effective equal 9.91. Then the limit state for fracture is 0.75 times 65 times 9.91 equal 483.1 kip. So in fracture, this section can resist 483, and in yielding, this section can resist 598.5. So as you can see, the design strength is the lesser of the two. The lesser of the two is the design strength. If you are asked to check the block shear, we can check the block shear and see. Okay, if the block shear is more than this or less. If the block shear is more than this, then this is your limit state. If the block shear give you a strength lower than this, then the block shear strength is the design strength of this section. Okay. Okay. Then one more thing, maybe we talked about it in the next lecture, but I'm gonna briefly touch in case. This is connecting elements for tension members. If you have a connecting elements, the plates that are used to connect the elements at the end, the plates that they can use the connect to connect the elements at the end, they have two limit states. There is yielding and there is fracture. Yielding is the same as for the tension member. It's 0.9 A gross Fy. But remember, usually the Fy may not be the same for the section. And for fracture, phi equal 175 and AN F ultimate. You see AN F ultimate. There is no A effective. There is no U. So it's just the fracture limit state will be 0.75 times AN times FU. Easier than the tension member. The tension member you have 0.75 times A effective, which is UAN. Here there is no U. All of the connecting element is the stress is uniform. But here there is a condition on AN. How much you can take AN? It must be less or equal 0.85 A gross. In other words, you calculate AN. If AN is more than 0.85 A gross, you use 0.85 A gross. If AN is less than 0.85 A gross, you use AN that you calculated. Good. And there is a straightforward example to calculate the two plates that are connecting the tension member. So you have a W shape here, and there is two plates, 3/8 of an inch times 12 the plate. The 3/8 is the thickness, the 12 is the width of the plate, and he's asking you to calculate the strength. Remember, if this is P ultimate, if this is the load applied, each plate is transferring half of that load. So how much the strength here will be? The yielding is straightforward 0.9 times Fy times the area, which is he's calculating for the two plates. As you can see, 2 times 3/8 times 12, he get 405. And for the two plates, he's calculating, he's subtracting how many bolts he has. You have 2 in each plate, so you have to subtract 2 in each plate. See, minus 3/4 plus 1/8, that's the diameter we take. We always add 1/8 of an inch times 2 because we have 2. Then there's additional 2 multiplied for on the outside, it means for the two plates, times the 3/8 is the thickness of the plate. So you get this area, you calculate the AN 7.65. AN here must be less than 0.85 A gross. So you check that. See, 0.85 A gross equal this. So it's less than 7.65. So he used 0.85 A gross, and he calculated the fracture limit state 0.7565 times AN, which is 372. So the design strength is always the lesser of the two. So we get 405 in yielding and we get 372.9 in fracture. So this is the design strength of the two connecting plates. Okay, with that we conclude the subject of the section. Basically is how to calculate U. How to calculate U, as I told you, it's the table in the specification section, which is table D 3.1. Table D 3.1 has all the cases, and also has on the right column on that table, it has explanation how to get what to take X bar and L and all the cases. And the slides or the handouts I give you, they are just basically explaining those cases in that table and some examples. Okay, so I'll see you in the next lectures.